Topic 3.05 Evaporation and Vapor Pressure. Ooh, can hardly wait. Well, last time you learned about gas behavior. The time before that, we took a look at how much heat it takes to make a phase change from one to another. The time before that, we looked at what these phase changes were. Now we're going to focus in on one very special phase change. It's a phase change that happens in between phase change temperatures. And we're talking, of course, about evaporation. Couple of questions we're going to answer during this. Why do some foods come with special cooking directions for high altitude? And because rice and beans take so long to cook, how can we make them cook faster? How do we get this rice and beans onto our plate faster? So here we go. Evaporation. What is it? Well, evaporation is simply when surface molecules of a liquid or a solid can escape to form a vapor phase. We're going to assume for the purpose of this lesson that it's the liquid that's evaporating. A closed system is a system that you have sealed up so that nothing can get in or out. So if you take an Erlenmeyer flask and you have your system inside the flask and you put a rubber stopper on it, then nothing can get in or out. As long as you don't add or remove any heat, it will remain a closed system. An equilibrium is a state at which the rate of two opposing changes are equal. So, for example, imagine yourself walking on a treadmill. You're walking forward on the treadmill at the same rate that you're going back. The treadmill is taking you backwards. And so the net effect is that you don't go anywhere. But you still have two opposite changes that are happening at the same speed. That's equilibrium. All right. Vapor-liquid equilibrium occurs when you have a liquid evaporating in a closed system. The vapor molecules will build up in the container, and since the system is closed, the vapor molecules cannot escape. The molecules will collide against the container wall, and this will exert pressure above and beyond the pressure already in the flask. So if the pressure in the flask was, let's say, 100 kilopascals, the pressure in the flask will increase as vapor molecules add to the gas already in the container. So as more gas molecules form, this pressure will increase. But there is a limit. As you may remember from earth science, air can become saturated with water vapor. There is a point at which air can no longer hold more water vapor. And at that point, the dew point, the water vapor begins to condense. When the molecules condense and rejoin the liquid, as this process moves along, the rate of evaporation will equal the rate of condensing. The rate of molecules entering the vapor phase will equal the rate of molecules leaving the vapor phase. So that means the amount of vapor above your liquid will remain constant over time. If you measure the pressure once this happens, that's the vapor pressure. So when the rate of evaporating equals the rate of condensing, you've got equilibrium. And notice that I've got a double arrow here showing that both are happening at the same time and at the same rate. This is the point where you can measure vapor pressure. So the pressure exerted by a liquid's vapor in a sealed container at vapor-liquid equilibrium, that is the definition of vapor pressure. And you can find it on reference table H. We'll take a look at that momentarily. Reference table H gives you a graph which has given temperature and vapor pressure. And so you just read the graph like you would read any graph. Here's the graph. We have temperature along the x-axis and we have vapor pressure along the y-axis. And if you remember our lesson on graphing, this makes perfect sense because the vapor pressure is going to depend on the temperature. So the vapor pressure is the dependent variable, making temperature the independent variable. And this measured the vapor pressure of 4 different liquids: propanone, which is also known as acetone or nail polish remover; ethanol or ethyl alcohol, which you'll find in wine or beer or even in 10% by volume gasoline; Water, of course, and ethanoic acid, a dilute solution of which is known as vinegar. So, what is the vapor pressure of ethanol at 60 degrees Celsius? Well, if you notice on the x axis, every square represents 5 degrees Celsius: 50, 55, 60, 65, 70, 75. So 60 degrees Celsius is here. And if we move up to the line for ethanol and then shoot over to the y axis, what would that reading be? Well, you remember from the graphing activity that the axes do not have to have the same size scale. On the x-axis, you're increasing by 5 with each interval. But on the y-axis, you're increasing by 10 for each interval, which means this is 40, this is 50, and therefore that will be about 47 or 48, somewhere in that line. And so we start at the 60-degree line. We move up to the ethanol line. We move over to the y-axis, and then we estimate, like we would with any measuring device, the vapor pressure. And because this is marked to the tens, we can estimate to the nearest ones. So 47 or 48 would be okay. 46, maybe pushing it a little. Definitely not 42, definitely not 49. Now, we can do that for any of these liquids. We can also use this reference table to determine the boiling point of a liquid. You see, below the boiling point, only the surface molecules have enough energy to escape to form a vapor. At the boiling point, every molecule in the liquid now has enough energy to form a vapor, which is why you get vapor bubbles forming at the boiling point. So the boiling point is the temperature at which you can sustain bubbles. Now, have you ever blown up a balloon? The reason you can do that is because you are able to blow into a balloon with more pressure than the outside atmosphere is pushing against that balloon with. Now, if this was not the case, if you could only muster a little less pressure than the atmosphere, you would not be able to blow up that balloon. The atmosphere would flatten that balloon and you wouldn't be able to inflate it. So you can only have bubbles if there's at least as much pressure in that bubble as there is surrounding that bubble. Otherwise, the bubble will get squashed. So at the boiling point, the vapor pressure of the water has to equal the pressure of the surrounding air. That's the only way you get bubbles. So these vapor bubbles will form because they have enough vapor pressure to do so, rise to the surface and burst and release their vapor. So again, this can only happen when the vapor pressure of these bubbles is at least as high as the surrounding air pressure. So, what is the boiling point of ethanoic acid when the air pressure is 80 kilopascals? Well, water's vapor pressure will be 80 kilopascals at a temperature of 100, 105, 110 degrees Celsius. At 110 degrees Celsius, the vapor pressure of the water will equal the pressure of the surrounding air. And therefore, the boiling point of water at 80 kilopascals, no, not water, ethanoic acid, will be 110 kilopascals. No, degrees Celsius. Wow, I'm really messing up my units here. 80 kilopascals, 110 degrees Celsius. Yes, that's the boiling point. Okay, so again, start at the 80 kilopascal line on the y-axis, move over to the ethanoic acid line, and drop down to the x-axis. When the vapor pressure of the liquid is equal to the pressure of the surrounding atmosphere, that is the point at which the liquid can boil. Normal boiling point is the boiling point at normal atmospheric pressure. STP, the temperature's 273, the pressure's 101.3. You'll notice on reference table H that there is a line for 101.3 kilopascals. That's there for a reason. So normal boiling point is the boiling point under standard pressure. So boiling point can change based on pressure, but the normal boiling point is the boiling point that you would see on an average day at sea level on planet Earth. So the normal boiling point of water will have the same vapor pressure as normal pressure at a temperature of 100 degrees Celsius. Because what you do is you start at the 101.3 kilopascal line and you just simply drop down once you hit the water line. Now, water's normal boiling point is 100 degrees. Now, that's at sea level. What if you were to move to higher elevations? Let's say you were to move from near the coast to, let's say, the Rocky Mountains. Now, the Rocky Mountains are much higher than sea level. So, what happens is at higher elevations, there's less air above you. Less air means less pressure. Less pressure means that water does not need as high a temperature to make its vapor pressure equal to the surrounding air pressure. And this will cause water's boiling point to decrease, requiring you to need special cooking directions for high elevations. What if you want to cook that rice and beans faster? Easy. Put it in a pressure cooker. In a pressure cooker, the pressure will increase. And if the pressure increases, then water will need a higher temperature to equal the higher pressure, raising the boiling point, cooking the rice and beans at a higher temperature, which means they'll take less time to cook. So propanone's normal boiling point would be 56 degrees Celsius. This is a pressure cooker. Some of you may have this at home in the form of either a dedicated pressure cooker or an Instant Pot. Instant Pots can act as slow cookers or pressure cookers. And the idea is you put your food in here, you seal it up, and the excess pressure will bring the boiling point up, cooking your food faster. So you put them in a pressure cooker, you put the water in with the beans, you seal it up, and then the water will boil at a higher temperature, cooking your beans faster. You'll notice on this particular ingredient list here, it says to bake 35 minutes, turn the chicken, bake about 15 minutes longer or until juice of chicken, chicken juice, yummy, is clear when the thickest piece is cut to the bone. 100 degrees Celsius, 100 degrees Fahrenheit for the breasts, 180 degrees Fahrenheit for thighs and drumsticks. The reason why you want to get the temperature that hot is to kill any bacteria, because chicken has salmonella, and salmonella can really do a lot of damage to you. So you want to have the temperature of the meat high enough so that the bacteria is rendered inactive. It kills the bacteria. Now, the normal boiling point for water is 212 degrees Fahrenheit. That's 100 degrees Celsius. But at higher altitudes, the boiling point of water is lower. And remember, once you hit the boiling point, the temperature does not go up any further, no matter how much heat you add to it, which means that you're going to be cooking this food at a lower temperature. So instead of baking for 35 minutes, you'll need to bake it for 40 minutes. And then instead of baking it for an additional 15 minutes, you'll need to bake it for an additional 20 minutes. This will help to make sure that the temperature of the food gets hot enough to kill the bacteria. So at higher elevations, there's less pressure. Less pressure requires lower temperatures to boil, which will require these longer cooking times to make sure that the food will cook. And that is everything you need to know about vapor pressure and boiling point. Next time we meet, we're going to be taking a look at gas laws and ideal gas behavior. Thank you very much for joining in today, ladies and gentlemen. And until next time, bye!